Hi everyone, today's lesson is on the third of the four conics, which is the hyperbola. It has a lot of similarities to the ellipse, and it's very easy to get some of the similarities and differences confused, so I will try to point those out as we get to them. We're going to talk about the definition of a hyperbola, what the graph looks like, and what its important features are, what the two different formulas are, and then how to get the features from the formulas. So let's start with the definition of a hyperbola. It happens to be the set of all points such that the difference of the distances between two fixed points is constant. If you're not done writing, just pause the video real quick, write it down, and then come back. All right, this definition is almost completely the same as the ellipse definition. The only difference is the word difference. The ellipse definition says that the sum of the distances between the two fixed points is constant. The hyperbola says that the difference is constant. And I'll outline what that looks like as we draw the picture. So I'm going to draw a rather large picture because there's a lot of stuff to label on this thing. So we're going to create a hyperbola. We're going to go ahead and center it at 0, 0. It just makes life a lot easier in this case. The center of the hyperbola is here, and it is h and k again. I will label it in just a minute. A hyperbola has distances in the horizontal direction and in the vertical direction. Now, in the ellipse, horizontal was called major, vertical was called minor, etc., but it's different for the hyperbola. The hyperbola only has two vertices, and I'm going to go ahead and draw the hyperbola itself in black so it kind of stands out. So here is a vertex, and here is another vertex. And the line that connects the vertices through the center is called, I'm going to try to make sure I have enough room to write all this stuff down. This is called the transverse axis. And it happens to be 2a units long. The distance from the center, I'm going to go ahead and put the center in here, out to a vertex is a, just like it was on the ellipse. So those two things are similar. But the transverse axis is the line that connects the two vertices to each other. Okay, now the ellipse has two vertices, top and bottom, but the hyperbola does not. But there are some definitive points that you need to be aware of. So let me make a change real quick. I'm going to change colors. Let's go to green. So this line, oh, didn't change. Let's go to dark green. So this line here, from here down to here, is b units on each side, just like it is with an ellipse. And this is called the conjugate axis. So the two axes for a hyperbola are not the major and minor. They're called the transverse and the conjugate axis. Now, you may be thinking, well, why do you even need that conjugate axis? What happens now is that you take those measurements once you have them and you draw a box, dotted line box, that goes through those 4 points, and those 4 points happen to be the midpoints of the rectangle. Sometimes it's a square because A and B in this instance can be the same size. Now, once you do that, you are going to draw diagonals through that box that extend beyond it. And these diagonals are what determine the shape of your hyperbola. And these diagonals have a special name, and they are called, and try to write it so it's not in the way, asymptotes. A-S-Y-M-P-T-O-T-E. So it has two asymptotes. An asymptote, by definition, is a line that a graph gets very close to and does not cross. The exponential function has an asymptote, the logarithmic function has an asymptote, and this conic has an asymptote as well. The curve itself goes through to vertices, does not ever go inside the box, and it hugs the asymptotes as it goes out. So it curves around like this and like this on the right, and then does the same thing on the left. So the black graph is the hyperbola. I'm going to move this word vertex really quick because I can. The two fixed points are the same two fixed points that they were before. They are the foci. But I haven't drawn any foci on here, so let me put those in. They happen to be here and here. They are on the same line as the transverse axis, but beyond it, inside the curves of the hyperbola. So the distance from the center to the focus, here's a focus, that distance is C as it was before. Now on the ellipse, the focus was on the inside. On the hyperbola, it's kind of on the outside. It's outside of the box. So let me see if I can explain a little bit more what I was talking about with those distances. If you pick any point on either one of the two curves, I'm going to pick this one right here. And you measure the distance from there to one focus, and then you measure it from there to the other focus, those distances, and you subtract them, it will be the same number no matter which point you choose on the curve. So if I called, let's pick another color, let's pick this orange. If I called this P and I called this one Q, P minus Q will be some constant for all points on this hyperbola. So if I picked a different place on the hyperbola and I measured P and I measured Q from that point to each focus and subtracted, I would get the same answer as I would in this case. So that is the setup of a hyperbola. Those are the important features. So now let's talk about the formulas for the hyperbola. And once again, they are the same as before. You have the general form, which is the same general form as before. I'm going to move it up some more. It's ax squared plus cy squared plus dx plus ey plus f equals 0. All the letters are capital except for the x and the y. But the thing that makes it a hyperbola is that a and c are opposite signs. If you saw an equation in the general form and you noticed that a was positive and c was negative or vice versa, that is an automatic indicator that that is the equation of a hyperbola. That's how you know. Now, the graphing form. And just like the ellipse, there are two graphing forms based on whether the vertices are horizontal or if they are vertical. The equation is almost completely the same as the ellipse. So as soon as we're done writing them down, we're going to take a moment and talk about how similar they are and what the similarities and what the differences are. So the first equation is x minus h, the quantity squared, over a squared, minus y minus k, the quantity squared, over b squared, equals 1. And this happens to be for what we call a horizontal hyperbola, where the two curves, like the picture above, open left and right. And this is what we call a horizontal hyperbola. What makes it horizontal? The fact that the x fraction is the positive fraction. Whichever fraction is positive determines which way the hyperbola opens. So the other equation has the a squared and the b squared in the same places, but the numerators switch. Y minus k squared over a squared minus x minus h squared over b squared equals 1. This one opens up and down. And this is what we call a vertical hyperbola. Now, let's stop for a minute. If you go back and look at your ellipse formulas and just take a quick assessment, what are the differences between this one and the ellipse one? The number one difference is the fact that this one says minus. If it says minus, it's a hyperbola. If it says plus, it's an ellipse. That's the number one difference between the two formulas. The other difference is the fact that on the formulas for the ellipse, the A and the B are what switched places, not the X and the Y. Here, the numerator switched places, and that's because the positive fraction determines the direction it opens. If the positive fraction is the Y, it opens in the Y direction. If the positive fraction is the X, it opens in the X direction. Now, also with the ellipse, we said that A was always bigger than B. A is not greater than B all the time for these problems. A could be equal to B, but A always is first. It's on the positive fraction. It is under the positive fraction. Okay, so don't assume that A is the bigger the denominator. 99% of the times, if you have it written in this form where you have a fraction minus another fraction, A is always the first denominator. And A will tell you which direction the vertices are. So now we're going to move on and we're going to take some problems that are in graphing form and we're going to find the features that we need to find. So I'm going to turn the page. We're going to do an example. We're going to find the center, A, B, and the vertices. We're going to find exactly where the vertices are. So we're going to do two examples. First example is going to be x minus 2 squared over 16 minus y plus 3 squared over 9 equals 1. All right, so we need 4 pieces of information. We need the center, we need A, B, and the vertices. Now the center is found exactly like it was on an ellipse. Remember, insiders lie, so you're looking at the numbers inside the brackets with X and Y to find your center. The center here is positive 2, negative 3. The minus sign between the fractions has no bearing on the center. All it does is tell you that it's a hyperbola. Based on what I told you on the previous page, what is A? A is the square root of the positive fractions denominator, which in this case is 4. B is the square root of the other denominator, which in this case is 3. Now you don't have to write down the square root of 16 and the square root of 9. You could just write A equals 4 and B equals 3, and that's fine. Based on the way this looks, is this a horizontal hyperbola or a vertical hyperbola? Because the x fraction is positive, this is a horizontal hyperbola. So this is horizontal. So what we do to find the vertices is we take the center and we add A to the horizontal component. Now think about that for a minute. Which variable is horizontal, x or y? X is. So we're going to take the A value and we're going to add it to the X value of our center. Add and subtract. So we're going to write it as 2 plus or minus 4 comma negative 3. The negative 3 does not change. So that means we go 4 to the right and 4 to the left to find our two vertices. So this comes out to be 2 plus 4 is 6, negative 3. 2 minus 4 is negative 2, negative 3. And there are our two vertices. Now, if you're having trouble picturing what I'm talking about, let me kind of give you a graphic of this. So our center is at 2, negative 3. There it is right there. Because x is first, that means it's going to be a horizontal hyperbola, which means we're going to have to go right and left to get our two vertices. So since A is 4, that tells me that I'm going to go 4 units to the right. 1, 2, 3, 4. There's my right-hand vertex, which is the 6, -3 that I wrote right here. And then I'm going to go left. 1, 2, 3, 4 to get my other vertex, and that left-hand point is this one, -2, -3. Some of you can just do it this way. I'd like you to get to that point if you can, but if you're having trouble understanding the math, draw the picture. It doesn't hurt. It shows you better where those points are and kind of gives you a visual representation of what's going on. All right, let's do another example. This is one actually for you to try. Y minus 4, the quantity squared over 4, minus x squared over 81 equals 1. I would like you to give me the center, A, B, and the vertices. So I would like you to stop the video, try to do this one yourself, and see if you can get the correct answers. All right, here are the answers to this problem. The center is at 0, 4. You've got to be careful. This is a tricky one. Even though the 4 comes first in the problem, it's with the y, so it is the y value of your center. So the x one, since it doesn't have a number with it, is a 0. Y is 4. Now, hopefully you got your A and B right, even if you had your center backwards. A is 2. It's always the first denominator square rooted. B is 9. This is a vertical. Why again? Because the y comes first. And since the y comes first, we take our A and we add it to the y. So 0, 4 plus or minus 2. I say add, but it's really add and subtract. So to simplify that, you get 0, 6 and 0, 2. The final thing we're going to talk about is how to change from general form to graphing form. To change from general form to graphing form, we're going to do exactly what we've been doing on the last 2 lessons, and that is complete the square. Now the complete the square here is 95% the same as before. It just has one slight change. I'm going to highlight that in red when I do it. It's going to be almost exactly like the ellipse except for this one little bit. So we have 9x squared minus 4y squared. Notice the difference in signs there. Plus 29 equals 54x plus 16y. Now this problem is all out of order. It's not even in true general form. That's the first thing we're going to have to do, is to put it into general form. So we have 9x squared minus 4y squared minus 54x minus 16y. Notice they both changed to negative. Plus 29, because the 29 didn't move to the other side, equals 0. All right, from here we do exactly what we did before. We take the 2 terms with x, but we must pull out the leading coefficient a. It must come out of the problem. So 9 bracket x squared, and then what does negative 54 change to? Negative 6x, put your plus blank, close your bracket. First change from the other way. Notice what's in front of y. It's a negative 4. So negative 4 must come out. Negative 4 bracket. Y squared. This is tricky. Notice you have a negative 16y here. You pulled out a negative 4. What goes here? It is going to be a positive 4y. Now think about that. You have a negative 4 times a positive 4. If you redistribute, that gives you negative 16. This sign has got to change. So now we put our plus blank equals, move the 29 over, it becomes negative, and then put your 2 blanks on the right-hand side. From here, it's exactly like before. 9, double bracket. Remember that the brackets must match. If the number in the bracket is -6, what goes in the two brackets here? That would be -3 and -3. The number that goes in the blank right here is +9, but +9 does not go on the other side. What goes on the other side? 81. Remember that it is going to be 9 times 9 when you redistribute. For the next step, it's -4 double bracket. You don't need to worry about the minus sign on the 4 anymore. You've already taken care of it. So we have y and y. What's in the bracket is +4. So what goes in the 2 below it? +2, +2. On the line in the blank is a +4. Be very, very careful. What goes on the other side? -16. Because you're multiplying -4 times +4. So we have on the left 9x minus 3, the quantity squared, minus 4, y plus 2, the quantity squared, equals -29 plus 81 plus -16. If you put it in the calculator, you will get 36. All right, are we done? Nope, we're not done yet. It has to equal what number on the right? It has to equal 1. So we're going to divide every term by 36. So the right-hand side is going to say equals 1. Now, the way I like to look at this is 9 and 36 here. That reduces to 1 and 4. So this is going to be x minus 3 squared over 4 minus, do the same thing again, this is 1 and 9. This is y plus 2 squared over 9 equals 1. And now I am in graphing form. Can you tell me the center? It should be 3, -2. A is 2. B is 3. Is this a horizontal or a vertical hyperbola? It is horizontal. So the vertices would be adding the a value to which letter? You're adding the a to the x. So it's 3 plus or minus 2, comma -2. So the vertices would be 5, -2 and 1, -2. So there you go. There's all your pertinent information right there. Okay. Now, your assignment. If you are doing, let's put it over here. I'm going to write it in red because so it'll stand out a little bit more. You're doing the Griffith book. This is section 1.5, page 14. If you're doing the Delta book, it is section 1.05, which is on page 20. I want you to do problems 2 through 9. Now, in the Griffith book, you can either do the odds or the evens. The Delta book, do a good sampling of 2 through 9. I don't remember exactly how long those problems are. All right. Let me know if you have any questions, and good luck with this assignment.